and let me make a co-host.
Yeah, we can wait a few minutes before we start. I'll also wait to see roughly what the audience is. I mean, we can adjust exactly what we talk about and stuff depending on precisely what the audience is. But anyway, yeah, I'll. How have things been for you during the pandemic, Juven? Has it been okay, bad, really bad, okay, good,
yeah,
really good?
I'm actually trying to juggle 6 balls now.
Oh, really?
Juggling,
okay.
yeah.
That's
one thing. That's one thing I can do.
That's good. Good to hear.
I try to improve myself.
That's great.
In any possible aspects, hopefully. And feel free to share a screen if you want to test.
Sure. Yeah. I'll do that. I'll do that right now. Just 1 second. I think it says I'll stop others screen sharing.
Please.
Should I just do that? Okay.
Yes, please.
All right. Let me. Just 1 second. Hold on 1 sec. One second. Yeah, that's good. All right. Can you see the screen okay?
Yes, perfect. By the way, one reason we don't want to spend extra time for you is because I saw that you have a previous talks before, so you might already have a slides already, right? So maybe we don't bother you to prepare another talk.
Oh no! I added a few things for fun. So I added a number of things for fun. And actually, there's some stuff that in the previous talk, I think that maybe you saw and didn't get to that I think I'll try to discuss. I'll try to discuss a somewhat complementary set of things to this one.
By the way, Nima, your screen is gone. No?
Oh, sorry.
I can.
There we go. Okay, is that okay?
Yes. people might gradually join in, and I think maybe we can gradually start. So let me start recording. Welcome everyone to Harvard CMSA Quantum Math and Physics seminar series. Also good evening, Shabbat. It's our great honor to have Professor Nima Arkani-Hamed from IAS Princeton. She'll be speaking about UV and IR and effective field theory. It's partly related to his previous talk at the all the effective field theory seminar series, maybe in January this year. And I saw this a bit pity that this talk is cut short. So today we want to welcome him again to maybe address this issue. I think a lot of quantum matter people would like to understand whether anything that they can do on quantum matter also can give rise to gravity. And certainly there are a lot of no-go theorem people know, but it would be nice to have some discussion about this, especially quantum matter people may want to care what might be what lack of. So I think Professor Nima Arkani-Hamed can feel this goal to tell us this story. So let's directly welcome Nima.
All right, well, it's really wonderful to be able to join you guys at the CMSA again. I was giving a very different talk around 3 weeks ago. And indeed, as Juven said, I was, I've been, of course, as many people thinking about this general topic. It's a very deep, old, important topic, and it's impacted various aspects of my own work in many ways over the past 20 years. And back in January, I gave a talk both about the sort of general subject as well as some new opportunities in exploring more concretely and maybe more surprising aspects of this, or some new aspects of this UV-IR connection.
By the way, Nima, excuse me, Nima, your camera is not on in case you want to show yourself.
Oh, really? Sorry about that.
Otherwise,
sorry. Yeah.
It's good.
Is that okay now?
Yes. Okay,
all right, great. And indeed, as separately, there's some overlap with the general subject, of course. But Juven and I have had many discussions over the years about the sort of challenges of thinking about the actual world around us as somehow a long-distance description from some condensed matter system. And the issues are at some level related to each other. So I'll say a few things about that as well, sort of early in the talk, and again say what I think of as some interesting concrete challenges and maybe opportunities also for pursuing that point of view. But just to begin with, let me remind you of the sort of glory of the usual Wilsonian paradigm for effective field theory. By the way, Juven told me this might be a somewhat broad audience, so feel free to interrupt me at any time. I've tried to intersperse, with that in mind, I've tried to intersperse throughout the talk both some sort of large-scale general things as well as a number of concrete things that might prick your interest if you're a little further from the subject. But what is this glorious Wilsonian paradigm of effective field theory? Well, at the most basic level, it's the seemingly very intuitive and obvious fact that we don't need to know all the details of microphysics in order to talk about physics in a meaningful and useful way at longer distances. And of course, this is an ancient idea. We teach it in school when we learn about Newton's laws. We don't have to keep track of all the atoms and molecules in a stone when we throw it. We use effective coordinates like the center of mass of the stone, for example, and have effective laws for those emergent properties of macroscopic aggregates of matter. And similarly, we don't need to know all about the details of water molecules in order to describe the motion of waves on the surface of the ocean. This is a very familiar notion in classical physics. What made it more confusing, at least in the 1940s and 1950s in the context of quantum field theory, is that quantum mechanical fluctuations can port information about physics at much smaller distances to much larger distances. There are logarithmic corrections to everything in even weakly coupled quantum field theory, and that confused people for a long time until Wilson came along and essentially figured out how to describe the physics, not organizing or understanding sort of graph by graph in perturbation theory, but scale by scale. imagining looking at physics at very small scales and gradually zooming out to get an effective description of physics at longer scales. And Wilson, and as well as Steven Weinberg, really emphasized this idea that whatever the underlying theory is, it doesn't matter what the underlying theory is, so long as it's compatible with quantum mechanics, and there's some notion of locality at long enough distances, locality and translational invariance. You don't even need Lorentz invariance for this part. It's guaranteed to be described by some kind of quantum field theory at long distances. And of course, this is a double-edged sword, because it means, on the one hand, we don't need to know all the details of high-energy physics in order to be able to talk about physics at lower energies, longer distances. On the other hand, it's very difficult to learn about high-energy physics. You need a microscope to probe short distances. Now, this Wilsonian picture, I want to stress, is fundamentally Euclidean. It's sort of well-defined in Euclidean space. In fact, the whole notion of the separation of scales, short distance and long distance, is a fundamentally Euclidean idea. And also, this paradigm was really born in condensed matter physics and is beautifully borne out in condensed matter physics as well. But as I like to say it, the world is not a crappy metal. And what I mean by this is that there are aspects of our actual world that are fundamentally not like these things that go into the Wilsonian picture. There are two of them. At the most basic level, the world isn't Euclidean, but it's Lorentzian. And of course, if you're working within the paradigm of local quantum field theory, this is a technicality, in the sense that we can begin with a theory well formulated in Euclidean space and get the physics that we want by analytic continuation to Lorentzian signature. Although that is always struck many people as kind of an odd way of doing things, given that the world actually has things happening in it and actually has time and is actually Lorentzian. But more than that, something that people have been appreciating more and more in the past 10, 20 years, is that the Lorentzian features, even of local quantum field theory, even of standard field theory, the Lorentzian aspects of the physics know things that are very difficult to see in the Euclidean picture. And it's basically because this idea that we have a clear separation between short and long distances is not so obvious in Lorentzian signature. After all, x minus y squared, the distance squared between 2 points, can be very close to 0, but the points can be macroscopically far apart from each other, so long as they're very close to the light cone. And I'll discuss this a little bit more in detail in a moment. That'll be one of the newer things I'll be talking about in a second. But something that has been appreciated more and more in the last 15 years or so is that this fact actually has interesting consequences on the structure of effective field theory that might be surprising to the naive Wilsonian effective field theorists. So here's an example. Imagine that we have, I've done as an example just electrodynamics here. We could even do a simpler scalar field theory. It's very generic phenomenon, what I'm about to tell you. So we start off with a Lagrangian, the usual Maxwell term. And imagine the leading higher derivative corrections that we might have coming from some unknown high energy physics. This is the first one, some coefficient times f to the fourth with various index contractions plus ... This coefficient can also be measured by doing some 2-to-2 scattering amplitude between the photons in the theory. So if I scatter the photons, there's some amplitude that goes like this coefficient and is a function of the Mandelstam invariance, the sort of energies of this process. They scale like the fourth power of the energies, and there's some constant there that has units of length to the fourth to make up for the unit. So this A is reflecting some details of of short distance physics. Now, super naively, if you're an effective field theorist, if you're a Wilsonian effective field theorist, you would say, well, we don't know anything about this A. We just have to go out and measure it from experiments, and it's somehow reflecting something about high energy physics. But in fact, we know something about A without doing any of that. And to see why, just imagine that you turn on a minuscule background electric field, a constant electric field. So we're not breaking translational invariance, and E is tiny. So in no way are we making this operator very important. Okay, we're turning on E an infinitesimally tiny amount, but we're turning it on everywhere in space, so in a translationally invariant way. Now, this doesn't break translation. So we still have a well-defined notion of speed of propagation of excitations around this background, but it does break Lorentzian variance. And it's very easy to show that, that while in the absence of A, the excitations, light in this case, travels exactly on the light cone, obviously. Any tiny A can either push you into the light cone or push you out of the light cone. Make the excitations go either in or out of the light cone. The fact if A is less than 0, the excitations propagate outside the light cone, and therefore we learn just from this argument that A must be positive. Okay, so that's something that's not obvious a priori to the Wilsonian effective field theorist. That even without doing it, having a microscope to go to very short distances and see what's there, just this fact that the physics isn't Euclidean but is Lorentzian, and that we can therefore access something about what's going on at ultra short distances by turning on this big background field and seeing whether the critical on the light cone phenomenon is pushed in or out, can tell us something about the signs of these higher dimension operators. So we'll talk about it a little bit more in a little bit, but this is saying that there's something very important about Lorentzian causality, and ultimately the origin of this positivity is also tied to unitarity. So these ideas of Lorentzian causality and unitarity are somehow tied up with positivity. Okay, so the world is not Lorentzian. This distinction between short and long distances in Lorentzian signature is not as clean, as obvious as it is in Euclidean signature, and that already has some interesting consequences on the structure of effective field theory that's not obvious a priori to the Wilsonian effective field theorists. More fundamentally and more deeply, the issues have to do with gravity. So we know that that there's some very basic, sort of very deep facts about gravity that we know ahead of time due to the following remarkable thing. So if you imagine taking a garden variety non-renormalizable theory, for example, the theory of the weak interactions before we knew about the W and Z particles, then if you'd ask someone what would happen if you collide the particles, for example, in the case of the weak interactions, it was electrons and neutrinos. What would happen if you collide electrons and neutrinos at energies 1,000 times bigger than the Fermi scale? And the answer is we have no idea. That's the point. There's a theory that has a dimension-full interaction. When you go to extremely high energies, it completely craps out. We have no idea what happens. And analogously, in gravity, we have a dimension-full interaction given by G. Newton. But the amazing thing is, in gravity, we know something already about what happens in incredibly high energy scattering. And it's the following remarkable thing, that extremely high energies, when the energies get well above, parametrically above the Planck scale, they no longer probe shorter and shorter distances. That entire reductionist paradigm that the physics has given to us fundamentally at very short distances, and by going to higher and higher energies, we get closer and closer to what the underlying stuff is, that's actually just basically wrong. We know that that's basically wrong in gravity, because what happens is you put the collision energy is so large that you actually make a large black hole. And the size of the black hole, when the energies are parametrically large compared to M Planck, increases with the energy. Okay, so that means that going to higher energies corresponds to even longer and longer distances. And so that means, in a very precise sense, we don't know that it's not like by going to higher and higher energy collisions, we can see the underlying stuff that things are made of. We can't do it. Instead, we make black holes. And furthermore,
Nima, excuse me, there's a question from Liu Jun.
Yes.
Please go ahead, Liu Jun.
Yes.
Can you go back to the previous slide?
Sure.
Yeah, I just want to, here I just want to make sure this sign, this positive sign of A has a Euclidean understanding, right? If I go to Euclidean signature and interpret this as an energy, then I require the energy to be lower bounded.
No, it doesn't have a direct interpretation in Euclidean signature because all of these ... dots could actually fix up any problem that you run into with the energy. You see, what the problem is in Euclidean signature is that let's say you talk about some excitation, right? I have some excitation. The problem is that, or I talk about its energy, anything you want to talk about, that in Euclidean signature, the leading F mu nu squared free part is already giving you something that's pushing you in the correct direction. And so these corrections are very small. And so the only way to make them important is to make the field big enough so that they can compete with the free part, but then all the higher derivative couplings are also important at the same time. Okay, so that's the typical situation. When you have higher dimension operators, the only way you can sort of learn something about it is if you find some process where for some reason the leading part gives you 0. And so the first correction that you get is from the subleading guys. In this case, in Lorentzian signature, we can do that. And that's just because there is something critical about the leading process. It's that it puts you exactly on the light cone. Because you're exactly on the light cone, any tiny correction from the higher dimension operators has the possibility to push you in or out. But you can really try. I mean, people have tried since these papers have been written. There are by now sort of Euclidean avatars of this argument, but they're very sophisticated, and they essentially end up finding some excuse, and they're true in conformal field theories, where essentially you use conformal invariance to convert the Euclidean question to one that gives you this that lets you think about it in this Lorentzian way. But for instance, you could say things like, I mean, we could maybe talk about this more in later, but you know, things like reflection positivity, all this sort of stuff that's supposed to guarantee the properties that we want. All of those, any interesting quantity begins by getting a large non-zero contribution from the leading term. And so it's hard to argue within the effective field theory that the higher order corrections can spoil it.
Okay, thanks.
Okay.
Nima, I have a naive
Yes.
comment. Just that I think when you mentioned this, the word is not a metal. I think what you really mean is not semi-metal. Just let me clarify the terminology. Because metal requires a finite density with a Fermi surface, but I think the density in our universe is 2 fields, so it's more like a semi-metal with a finite number of the flavor of the fermions, maybe like 15 or 16 fermions per generation.
Well, I did not. I meant nothing. I did not mean any technically correct thing by that statement. And in fact, I'll come back to say. I mean, I think well, anyway, let's come back to that sentence in 5 minutes. Okay. So okay, there are other well-known things. So. For instance, we know that, again, in typical local systems, the number of degrees of freedom scales like the volume, but we know when we have gravity that the maximum number of degrees of freedom in a fixed volume, that the maximally entropic object with a given mass is a black hole with that mass. So the sort of the number of degrees of freedom inside some volume is bounded not by the volume, but by the area in Planck units. And these are both sort of qualitative statements. There's a kind of sharper statement that's also associated with these, that when you have quantum mechanics and gravity, in a precise sense, there are no local observables. When we turn off gravity, we have all kinds of local observables, correlation functions, and so on. We can do measurements in a room, in a fixed size room, and we can make well-defined quantum mechanical observations by repeating the experiment over and over again and using larger and larger measuring apparatuses. To get arbitrarily accurate observations, but that's obstructed when we have gravity, because when we make our apparatus in particular bigger and bigger, it inevitably gets heavier and heavier, and it eventually collapses the fixed size room into a black hole, and we can't do the experiment over and over again. Okay, so there's some fundamental limitation there's a systematic error associated with any local observables. There are no local observables in gravity, and that makes it difficult to imagine that there is a local underlying theory behind it. Now, I've mentioned these two issues of the Lorentzian nature of the real world as well as the fact that we have gravity, and in fact, the constraints from these two ideas are related to each other. There are many ways. This is a topic that I could talk about for hours. Let me give you just one of them. For example, the fact that Lorentz invariance gives us a universality of a notion of a light cone, so that all speeds of light, all upper limits for all speeds are exactly the same, is something that's really crucial for a black hole horizon thermodynamics to make sense. So you might imagine, I mean, even without writing down concrete theories, and, you know, people have written down, even I've worked on funny theories that gave spontaneous breaking of Lorentzian variants and so on, that you might even let you sort of play with such ideas more concretely. But just to give you the rough idea, imagine that you have some theory where you have different species of particle that have slightly different speeds of light. So that means that in a black hole, that there would be slightly different horizons. Depending on the species, you'd have different different horizon sizes, and that's a disaster. The moment the notion of a horizon is not universal, you can violate the second law of thermodynamics, because the black hole will radiate the, let's say, particles A and B at two different temperatures, TA and TB, and you can use that to build a perpetual motion machine of the second kind. Okay, so the respecting the sort of sharp light cone associated with Lorentzian variance is actually related to the consistency of black hole thermodynamics, which is ultimately related to these holographic bounds and the UV-IR connection and all the rest of it. And there's actually a number of other sort of precise indications of a sort of some at least continuum that links these two ideas to each other. Let me mention a few of the things that I think have happened in the last 15 years or so. Of course, people have known about these sort of rough holographic statements for a long time. And of course, we have the precise notions of holography as in ADS CFT. But coming back to these rough ideas about the consistency of black hole thermodynamics and so on, I think many people for a long time, certainly for a long time, I believed that whatever the constraints were that were associated with this physics were not going to have any real teeth in telling you something very shocking or surprising about effective field theory, that likely any sort of two derivative normal effective field theory would satisfy all these rules, and only very special questions involving things like the information paradox and so on, very esoteric questions, you would need, these things would really show up. And I think something that we've been seeing in the past 15 years or so are sort of maybe more surprising constraints, conjecturally at least emerging, enforced by the consistency of black hole physics. So I won't go through this in any detail, but you might think that that if you have an object that carries a huge entropy, that there's a self-consistency reason that you should be able to see the sub things that the entropy is made of. And if we apply this to an extremal black hole, if we apply it to a Schwarzschild black hole, that's fine, because it's sort of constantly radiating things. And so you might imagine that after it finishes radiating, we can sort of, all the stuff that came out has something to do with the microstates that made the black hole. But if you have an extremal black hole, then an extremal black hole that has charge, then it can only decay if there are objects with mass to charge ratio smaller than 1 in Planck units for it to decay to. So that's a motivation for thinking that there's always got to be some state with mass to charge ratio smaller than 1 in Planck units. And for that state, gravity would be a weaker attraction than the electrostatic repulsion. So that's the so-called weak gravity conjecture. And if you think it's true, you might further think that the way it's made true is that corrections to the mass to charge ratio for black holes should actually push that mass to charge ratio down. The corrections from higher dimension operators should push that mass to charge ratio down. So you see, this again is making a prediction from very specific signs for the deviations from Einstein gravity. And in every known example in string theory and in other places where different sorts of universal corrections of this sort have been computed, people have found that it does indeed always push it in the direction that you would expect from this argument. And so this is actually an example of how these constraints having to do, so remember, I just told you a moment ago that there are constraints on higher dimension operators just coming from the absence of superluminality. So there's one question that you could ask. You say you take an extremal black hole and you imagine that there's an f to the 4th correction like this. What sign would it have to have in order for the mass to charge ratio of the extremal black hole to go down? And of course, it's exactly the same sign as you need from the superluminality argument. Okay? And that sort of thing has happened more and more. I just had a paper out last week about another aspect of this. But I think there's a picture something like this, that if we imagine the sort of the mass of charged states, if I plot the mass, and here's the sort of mass to charge ratio.
Excuse me,
one
Nima.
is, yes.
Sorry, there's one more question. Liujun,
Yes.
again.
Yes.
Sorry. Can we go back 2 slides again?
Sure. Just 1 second. Yeah.
I don't think. Oh.
Sorry. Yeah.
Yeah. So I just want to make sure here you argue that Lorentzian invariance is needed for thermodynamics to hold. Do you mean
Black hole thermodynamics? Yes.
Yeah, that's what I want to ask. You specifically mean black hole thermodynamics?
Yes, I specifically mean black hole thermodynamics. Yes.
But when you say black hole thermodynamics, did you already assume that black hole, at least classically, is described by general relativity?
Yes. So this is why I said that this could be. I mean, we could talk about this subject for hours. I really like talking about this subject. So to be really more precise about it, I should give you some context where you can build a theory where you might be able to spontaneously break Lorentz invariance and really do this in a way that you can find the black hole, have this discussion, and set it all up. We could talk about that. Those theories exist, have been studied. They're sort of interesting, sort of Higgs phases of gravity that you can study, at least as effective field theories. But the hint that there's something wrong with them is that they allow you to do crazy things like this. But I was sort of skipping to the near the end point of this discussion just to give you some intuition for why that is. So indeed, there's something like black holes, GR, where we don't want to, we're imagining we're not completely screwing things up, but that maybe different species of slightly different speeds of light. How could it be so bad? 10 to the minus 10 different speeds of light. And it's bad. It's sort of fundamentally bad because the moment you mess with the universality of horizons, you allow these kind of perpetual motion machines of the second kind to be built. And there are many other examples of this type. This is just one of them that I wanted to mention.
Okay, thanks.
Okay, yeah. So here again, in the context of this weak gravity conjecture, you can imagine there's some sort of spectrum of basically particles. When the masses are enormous, there are extremal black holes. When the masses are small, they might be used in elementary particle states. You might imagine doing something like this in string theory. But when the masses are enormous, really enormous, there are some calculable corrections just from massless loops in the low energy effective field theory of gravity that you can show always pushes mass to charge ratio down. When the mass is a lot smaller, but still bigger than the Planck scale, there's a regime where this correction is dominated by higher dimension operators. Now, for that, you really need some complete UV complete theory, like string theory. But every time you check them in those UV complete theories, it always pushes it down. And then ultimately, when the masses are much smaller than Planck scale, they're just sort of elementary particle states. It might be string states. It might be states in whatever the low energy effective field theory is. But again, in all examples, there is always pushed down. But you see, it's part of a continuum. It's part of this continuous curve that's approaching 1 from below. And the reason given for why it's less than 1 has something to do with Lorentz invariance and causality way out here, and has something to do with the details of the UV completion of gravity down here. But it's part of a continuous story. So these are just a few examples where there's a link between the issues about blackaholics, gravitational UVIR, and the important constraints that come from Lorentz invariance and causality. Okay, so now, and I think this is the these are the questions that at least Juven and I have discussed over the years. In this light, about the sort of general question of whether we might imagine that our universe is actually the long distance limit of some kind of condensed matter system. So let me just phrase it as a bunch of question and answer. So question, can't we get some Lorentz invariant theories of gauge fields, et cetera, out of underlying lattice or condensed matter models? They're all these cool, beautiful things that people have done, especially over the last 20 years, where we see exactly this sort of thing happen. Gauge fields emerge at long distances. It's an underlying lattice model, but we get just QED at long distances. And what I would say to that is that this is an amazing thing. It was actually really amazing when it happened for the first time in the 1800s. And that's in fact the story of how Maxwell found Maxwell equations, and the entire story that led to the discovery of Lorentz invariance and special relativity went through this route. They had a mechanical model of the ether that at long distances produced a Lorentz invariant theory. This can happen classically. It does happen classically. Of course, we also know that it happens quantum mechanically with all these beautiful developments of the last 2 decades. But of course, there's a but, which is that getting Lorentz invariance for a single species of particle is relatively trivial. And that's because dispersion relations like omega squared equals c squared k squared at long distances happen all the time. After all, just take the waves on a rope. If I take waves on a rope, they're described by a wave equation. The dispersion relation is omega squared is some c squared k squared, the speed of sound in the rope. And there are corrections coming from the underlying, atomic spacing, lattice model, whatever it is. It goes like k to the 4th a squared plus ... But obviously, at long enough wavelengths, these are irrelevant. And so we get something that looks like a Lorentz invariant dispersion relation. After all, the wave equation that describes the waves on a rope is Lorentz invariant. And this, by the way, is why, at least in my view, when we teach, undergraduates about how dumb all those classical physicists were in the 1800s for believing in the ether, it wasn't that dumb at all. I mean, even that you can get Lorentz invariant equations out of non-Lorentz invariant systems. That happens all the time. Okay, so, but of course, there are 2 novelties. One of them is, again, quantum mechanics, that quantum mechanical fluctuations make it much more difficult to find accidental symmetries at long distances. If you're going to find an accidental symmetry at long distances, and that symmetry isn't present at short distances, you need something else that guarantees that all of the corrections, all the things that violate that symmetry that will correspond to dimensionless couplings or marginal couplings in the low energy theory are somehow gone. Okay, so that's a very significant constraint on the full theory for that to happen. And in fact, the difficulty is that now we know in our world that there are multiple species, every particle that we know of, and there's no symmetry that relates them that we know, totally different particles, electrons, neutrinos, quarks. There are multiple species. And there's no reason that from this accidental point of view, there's no a priori reason that all their speeds of light would be the same. In fact, in the standard model, these differences in the speed of light between different species are all marginal operators that break Lorentz invariant. I forget exactly how many of them there are, but there are order of 50 of these operators, and each of them is bounded to be less than around 10 to the minus 15 experimentally. Okay, some of them are bounded as harshly as 10 to the minus 25. And in fact, very recently, thanks to LIGO, we know that this is even true for gravity. That the speed of propagation of gravity and everything else is also the same, within roughly a part in 10 to the 15. If you haven't seen where these things come from, this number 10 to the minus 15 comes up over and over again, essentially because you look, for example, in this case with LIGO, you look to see that the gravitational wave signal and the light signal from some source arrive at basically the same time. Because it is traversing such a humongous distance, billion light years from us, because it's traversing such a huge distance, even a tiny difference in the speed would give rise to a large measurable time delay. And that's why we can put these incredibly stringent limits on the differences between the speed of different species. Okay, so if there's any kind of underlying idea, if we imagine literally, there's some underlying sort of condensed matter system, lattice structure, something that doesn't fundamentally have Lorentz invariance in our world, this is a challenge. It has to somehow produce operators. It has to produce all these different species that we have that do not at all seem to be related to each other. It's not like they're in some multiplet together, so they all have the same C. They seem wildly different from each other, and yet they all have exactly the same speed of light. All right, that's one challenge. Now, and that's a challenge, of course, is related to Lorentz invariance. Now, the second challenge, can we make gravity in 3+1 dimensions emerge from some 3+1 dimension underlying condensed matter system? After all, we can maybe even engineer theories that have gapless spin-2 excitations. So there are these beautiful examples that you can get emergent gauge fields, photons. Maybe we can get emergent spin-2 excitations as well. And here again, it's all these issues are related. The problem is that getting gapless spin-2 excitations does not at all say that you've gotten gravity. the relationship between the presence of massless or gapless excitations and the corresponding long-range force, that relationship is one that's forced on you by Lorentzian variance. Okay? In fact, there's a sort of beautiful picture I'm sure many of you are familiar with that Ed Purcell drew. This is a small variation on Purcell's picture for why it is that relativity plus the Coulomb law implies that you must have radiation. So this is a sort of famous picture where you imagine there's a charged particle that's coming in, and at this center point here, it bounces. So it's moving in this direction, but at this center point, it bounces. So that instead of going all the way here, it bounces and it's over here. So it's had a big acceleration. Why does this imply radiation? Well, locally in the neighborhood of the charge, the electric field lines are coming out. Okay, so they have to look like that. But far away, because of the finite speed of light, because of Lorentz invariance, it doesn't know. There isn't room, there isn't time for the things far away to know that the electric field lines should have been pointing to where the particle would have gone next. So the field lines far away would be centered on where the particle would have gone if it didn't bounce. And you plainly see that you can't connect up these electric field lines together unless you have this kink. And that kink is exactly this sort of shell of radiation that comes out from the charge. So anyway, this is a beautiful cartoon, not even a precise picture, but more generally, we know that the relationship between the long range force and the polarizations of the particles is one that's given to us by Lorentz invariance. If we have no Lorentz invariance, there's no reason the presence of a gapless particle has anything to do with the long range force, and therefore whether or not you can get gapless spin 2 excitations, linking that with gravity, and by this I mean gravity, like the thing that makes apples fall. These are only linked if you have Lorentz invariance. Okay, well, in a Lorentz invariant system, we have the Weinberg-Witten no-go theorem. Okay, so that we cannot have a Lorentz invariant theory, local theory, with any local operator in that theory interpolating and creating out of the vacuum what you might call a graviton. For a very simple, it's a 3-line argument, essentially kinematical argument, that we can't have sort of gravity emerge, gravitons emerge as some composite bound states, something like that, in an underlying Lorentz invariant system. And all of these things, when it comes to a gravity, I think are related to and somehow superseded by what I mentioned already, the sort of very deep fact about gravity, that there are no local quantum mechanical observables. No matter what the theory is, whatever the formalism, anything you want to imagine, this difficulty that when you build a larger and larger measuring apparatus, it gets heavier and heavier, and eventually collapses things into a black hole so that you can't talk precisely about local observables, is maybe the single deepest thing that we know about gravity. It was appreciated in the 1960s by very few people like DeWitt and Penrose that this had a dramatic implication, that if we're talking about asymptotically flat space-time, the only kinds of observables we could talk about are scattering amplitudes, not local observables that we measure in finite-sized labs, but experiments that start and end at infinity, where we can make the apparatuses bigger and bigger and move them off to the boundary in order to make precise observations. And of course, famously, since the late 1990s in string theory, now much more generally, we have the much richer playground of boundary correlation functions in anti-de Sitter space, where again, if you lived in this sort of this tin can cylinder of anti-de Sitter space, you can ping excitations on the walls of the can, and the waves crash into each other, come back out. You can measure those correlation functions at infinity. Those are the kind of those are the sorts of observables that we're allowed to talk about. And now, of course, famously in that context, the idea of some kind of condensed matter system giving rise to a world with gravity and so on is much more reasonable. Okay, so you could ask, what about a condensed matter system in d dimensions that is holographically dual to a gravity theory in anti-de Sitter space in d+1 dimensions, as we've already seen, for example, in the SYK model. And of course, this is definitely possible. It happens. It's fascinating, and it's interesting to look for more examples. But again, I would also say that there is a but here, which is that the really interesting theories of gravity in ADS D+1 are the ones that have a large separation between the ADF length and the Planck length. I mean, this is some region where there's kind of a reasonable flat space region with things that look like gravity, with normal apples falling, and you might imagine a kind of local person in there, not knowing that they lived in anti-de Sitter space, but just like looking like normal physics. Of course, it couldn't be our world. Our world is cosmological. Our world doesn't look like anti-de Sitter space globally. But that's kind of because of the details of cosmology. You might imagine that if we didn't know about the details of cosmology, we might be a person like this who lives in anti-de Sitter space. You can't tell that it's negatively curved. The curvature is 100 billion light years, but there's a large separation between the ADS and the Planck lengths, and everything is okay. And you could ask, could that somehow emerge from a one lower dimensional condensed matter system? That's absolutely fascinating, very interesting. But all known examples that do this trick of having a large separation between the ADS and Planck lengths so far are relativistic quantum field theories. This is perhaps related to the fact that somehow in the bulk, they have to give you something where all the speeds of light are the same, and et cetera, okay? But here it's conceivable there might be some new class of systems that we haven't understood yet, different ways of going to strong coupling, different ways of thinking about large N, which don't fundamentally need a Lorentzian variant description in D dimensions that might give rise to something that becomes a Lorentzian variant in D+1 dimensions. Okay, these are so if I go back to the two main ways in which the world is not sort of Wilsonian, it's Lorentzian, and we have this sort of UVIR connection in gravity. There's a third thing that I don't want to spend any time talking about here. It's a topic for yet another 2-hour-long talk. But we have encountered as properties of our vacuum what looks like a spectacular failure of the Wilsonian notion of naturalness, and that's the idea that if your effective field theory has dimensionful couplings with positive dimension, which are very important at long distances, then if there isn't any symmetry reason for them not to be there, you should expect that they're there on at a scale that's set by the ultraviolet scale of the theory. That notion works unless you finally adjust the parameters or do something in order to tune those relevant operators away. That picture works beautifully in condensed matter systems. It explains why we don't walk around and see random condensed matter systems close to second order phase transitions. We have to do something to the system to put them close to second order phase transitions. But somehow our universe has these two relevant couplings, the cosmological constant and the Higgs mass squared, and for these they're nowhere near their natural values. The cosmological constant is 120 orders of magnitude smaller than its natural value. If the ultraviolet scale is set by the Planck scale, the Higgs mass squared is 30 orders of magnitude smaller than that. And there are, in the case of the cosmological constant, there are sort of no good ideas for what could explain this. In the case of the Higgs, people had all kinds of sort of dynamical models and ideas, supersymmetry, symmetries that might explain the origin of the Higgs mass squared, and none of those have turned up at the LHC, and they're not completely dead. Those ideas are not totally dead, but I would say that if you turn into a pumpkin at midnight, it's 11:45 at the LHC. So they're under a severe pressure. And so this is another kind of experimental hint that not just for things way up at the Planck scale, but even right above our head at accessible length scales. The length scale associated with the cosmological constant is 1 millimeter. The energies associated with the Higgs mass squared are not the Planck scale. They're the energies that we're probing in experiments today, but that there's something wrong with this sort of Wilsonian picture already much closer to home. So if I go back to my first polemic, I think what I'd like to say again is that the world is not a crappy metal. It's not some sort of garden variety condensed matter system, and even maybe not one of the sort of less garden variety ones, but the ones that people in condensed matter physics have been all these beautiful, remarkable structures that they've been finding to produce these fascinating long distance effective field theories. that it has to be something even more exceptional than that. It has to be some kind of exquisite metal, not a crappy metal. And the sort of a concrete challenges. There are many challenges in what I said, but I think if I had to name one thing that would sort of convert me overnight, and I would sort of drop everything I'm doing and join this quest, is if it was possible to find a condensed matter system which produces totally distinct species unrelated by any global symmetries at all, that produce the same speed of that propagate with the same speed, have the same speed of light in their dispersion relation. In other words, that really gives you emergent Lorentzian variants in a way that's really meaningful, where all the marginal operators that would break Lorentzian variants, in particular all the differences in the speeds of light, are either zero or flow very rapidly to something which is extremely small as you go to low energies. Okay, all right. So that completes the sort of introductory part of the talk. I'm not doing so great for time, but maybe I can pause here. And before going on, well, so let me say what my plan was, but we can do parts of this. I wanted to mention sort of what I think of as three frontiers in this business, where yes.
Nima, some question. I think Sunset has a question. Yeah. Sunset, please go ahead.
Yeah.
Sunset.
Hi. So I have one comment on the previous point about examples where multiple species emerge with the same speed of light.
Yeah.
So I thought that the reason that we don't have such examples is because we don't know how to solve strong coupling problem.
Right.
So rather than it's a fundamental obstruction.
Well, right. I think I have nothing to say. I mean, but I think this is really what I mean, all sort of kidding and jokes aside, this is really what I meant. It's there has, if there's something like this, at least for this aspect of the problem. I mean, there's the aspects that have to do with locality and gravity and all the rest of it. Even putting that aside, just the sort of Lorentzian variant aspect, yeah, maybe there's some remarkable feature of some strongly coupled systems that we don't know about that produces Lorentzian variants. That would be spectacular. If that could happen, that would be, as I said, I mean, if I saw one example of that, I would do nothing but try to understand it. But yeah, I don't think we have any evidence at the moment either way, whether such a thing can exist or not. In particular, we have no positive evidence for it.
Mm-hmm. Okay, yeah, thank you.
Wait, for this issue, I just want to make sure. Suppose I consider, say, 2 + 1 dimensional large N QED in flavors of the arc fermions, and let me assume the UV Lagrangian has different speeds of light for fermions and the gauge field. Then I can do controlled calculation. I thought the result is at the end, at RG fixed point. At least the overall interaction will make the speeds of light to be the same, right?
Right. This kind of thing in 4 dimensions is just logarithms. In low dimensions, it can be powers, so that can be effective. In 4 dimensions, perturbatively anyway, it's just logarithms, and it's not nearly enough. So people did this in 4 dimensions. I mean, this idea goes back to Holger Nielsen in the 70s. He called it sort of order from chaos. You don't need anything, you just any theory you write down, and then indeed you just do loops, and with large N, like you said, it runs and it becomes Lorentzian variant at low energies. But in 4 dimensions, it's logarithmic running. Perturbative, it's logarithmic running, and that's not nearly good enough. I mean, for us, that is not nearly good enough. Okay, and also those examples still have very much a flavor of the species being closely related to each other. I'm talking about something like that would make quarks and neutrinos and electrons. I mean, things that are sort of in utterly disconnected sectors that have nothing to do with each other, apparently at low energies, nonetheless all have the same speeds. What you're talking about is really just that no matter what kinetic terms you write down, all the kinetic terms at low energies get dominated by one coupling in the low energy loops, and that makes everyone have the same speed of light. And that can happen, as I said, it's way too slow in 4 dimensions, but also it only happens in systems where everyone is closely related to each other by some symmetry that in the end is the same speed of light for everyone.
Mm-hmm. Thanks.
Any other questions?
Oh, by the way, let me make a comment. I think Nima, you probably meant to say the world we live in was all the consideration of gravity and all the issues that mentioned that maybe the idea from quantum matter may not be enough to address the full thing. But just to clarify, there's still room to improve from the current development of quantum matter. There could be mechanism that can be used in fundamental physics.
Look, that goes without saying. I mean, that's such an obvious thing that it
Yes.
goes absolutely without saying. I mean,
No
that there's so many of the greatest ideas in this subject have come in that direction, and the cross-fertilization now is probably, I imagine it's almost either as exciting, more exciting, comparably exciting to what it was when the similar things happened in the 60s. Of course, I mean, the intellectual overlap of the field is huge. I mean, I'm not an expert in these things, as you know, but even from the distance I'm at, it's obviously there's lots of fascinating things going on. The field theory phenomenon that are being uncovered are fascinating. Even aspects like the Nati Seiberg likes to emphasize to me that there are sort of cousins of UVIR phenomenon, not the ones that we apparently literally see with gravity, but still very interesting kind of exceptions to Wilsonian thinking that come out when you try to understand fractons, for instance, in a field theory language and so on. So it just absolutely goes without saying that the development in our understanding of field theory is benefiting tremendously from the sort of complementary point of view of thinking about phases of matter, especially the way of thinking about it in terms of thinking about what the state looks like, thinking about what the wave function looks like, patterns of entanglement, and so on. That's really something that condensed matter physicists naturally do, that high energy physicists do not do, and has been very, very stimulating. But what I'm talking about is really specifically the idea, the much more specific idea, basically in the sort of picture of Maxwell, or some 21st century version of the picture of Maxwell. Could there be underneath us right now, in this world, in our dimension, some underlying condensed matter system that gives rise to us? And that's the thing that, of course, I have no theorems, but what I was doing in this part of the talk, and I think this is the discussion that you wanted to have, Jubin, which is why I was I'm going through it. Nothing I say here is original at all. I mean, I think these are all things that other people have said more eloquently than me. But in any case, I certainly believe them. These are the things that look like the sort of major challenges to this picture. There's no go theorem, but there are already a few things that you could try to imagine accomplishing along the way that show that something magical is happening. But there seems to be some very large challenges to it.
Oh, thanks.
Okay, well, let's see. Jubin, how long do I have?
Well, typically, at least you still have a
maybe we can do the following. Do we want to stop and clap right now? I mean, I haven't really said anything yet, but we can stop and clap so that anyone who wants to decouple can decouple. I mean, of course, they could anyway. But
yes.
But should we stop and clap and then just take a 3-minute break, and then I can go on with whoever's left?
Typically the seminar is 90 minutes, so you are actually
typically
ahead.
90 minutes. Oh, never mind then. Okay,
and actually,
okay, sorry.
I imagine in your case it should be at least till midnight. Before midnight. So no worry.
Never mind. Sorry.
But I think we should clap also.
No. We don't need to clap. If you're not clapping yet, we don't need to clap. All right. Let me just go on. All right. Sorry about that. All right. So So I won't talk about all these things, but maybe I'll try to talk about the first two. At the meeting back in January, I talked more about the third one. And anyway, there's some local experts there at Harvard, like Andy Strominger, that knows all about these things, and many more interesting things besides that you could talk to. But what I want to do is talk about some of the things that we've been learning that are much more sharp and precise constraints on effective field theory that come from these sort of very basic physical properties like Lorentzian variance, we assume Lorentzian variance, really Lorentzian variant causality and unitarity. So we saw very small examples of that early on, that there are these positivities of higher dimension operators. But we're going to see many more things besides that. We're going to see a sort of infinite extension of that picture. And in fact, the kind of, if we group all the coefficients of higher dimension operators in effective field theory together, or even classes of them that correspond to 4-point operators, or would give 2-to-2 scattering amplitudes, the claim is that this infinite collection, this infinite set of coefficients actually have to lie inside a very sort of constrained geometric region that what some collaborators and I recently called EFT-hedra. And the second thing that I want to talk about is one more aspect of this IR-UV connection that is not, I've found, widely appreciated, which is the reason why it's difficult to UV complete gravity. And we'll ask some very simple questions about what a UV completion of gravity scattering processes might look like, and I want to show why another aspect of this IR-UV connection tells you why it's so difficult, and also why some very simple arguments suggest that any perturbative UV completion of this sort should look stringy. And I'll say a few more things about that. And the third topic I won't talk about. Okay. So we already saw that we've known for a long time in field theory that there is a connection between these ideas of locality and causality and unitarity, and the analytic structure of scattering amplitudes. In fact, at the most ancient version of this is just dispersion relations to prove why the index of refraction is always bigger than 1 in materials, for example. Okay, so we've known for ages that causality in the time domain is reflected in certain analytic properties, nice analytic properties of the Fourier transforms of 2-point functions in the energy domain. And that's generalized in some way that's still poorly understood to certain analytic properties of scattering amplitudes as a function of the complexified energies and momenta, somehow reflecting causality. So that has been something that people have understood for a long time. Something that's happened, at least in my own work over the past decade or so, is a kind of inversion of this, is that in studying many miraculous properties of amplitudes in a number of sets of theories, we've been discovering that the amplitudes appear to be the answer to very different kinds of mathematical questions. They're not fundamentally, in this way of thinking about things, associated with summing Feynman diagrams or anything like that. They live in a much more sort of alien seeming abstract space, but that the fundamental mathematical ideas in these spaces involve notions of positivity in an interesting way. And that you can extended notions of positivity in an interesting way, and that starting with these sort of more abstract pictures, you can see how things like locality, causality, and even unitarity emerge from these more primitive structures. And given that that's at least dominated my own work over the past decade or so, I decided with Yutin Huang and Jimmy Huang to go back and just think about this old picture where analyticity and positivity sort of emerges from locality and causality and unitarity, and to see if there's sort of more positivity there than we had noticed before. And indeed, there's an enormous amount of extra positivity there, and that's what I want to tell you a little bit about. Now, one reason for telling this to you, and one way that it connects to the story I was talking about before, is if you imagine somehow there's some underlying non-Lorentzian variant system, something that nonetheless gives us something, and the speeds of light all work out the same, and so on. You might imagine that it makes that happen at long distances, but that deep in the ultraviolet, it isn't true, right? So it's some very different thing. So that might make you think that that while the kind of leading long distance corrections would look like they're compatible with Lorentzian variants and all the usual rules, that maybe there's a way to distinguish between this idea and something that's fundamentally sort of Lorentzian variant and causal all the way up in some way. Maybe there's a fingerprint of that difference in the structure of the higher dimension operators. And so what I'm about to tell you is that the structure of the higher dimension operators are vastly more constrained than you would have naively thought. And I'll show you what those constraints look like. So that, of course, this is not experimentally practical now. We don't have access to many higher dimension operators beyond the standard model. That's the real difficulty of particle physics right now. We not only have not seen new particles, we haven't even seen higher dimension operators convincingly yet. Maybe the mu on G-2, if it holds up, will be a higher dimension operator that we've seen, but I'm not holding my breath for that. So we haven't seen any higher dimension operators, but at least in principle, you might imagine that we could someday discover higher dimension operators. And what I'm saying is that there are some constraints that those higher dimension operators must satisfy, infinite number of constraints they must satisfy, that is a direct consequence of this assumption of the standard picture going all the way up. And so any violation of that would immediately show that this standard picture is wrong. Okay, it would not necessarily, it wouldn't tell you that it's an underlying condensed matter system or something like that, but it will at least show you that it's possible for something to violate these rules, and they would show up in a very concrete way in measurements you can in principle make at very low energies. Okay. All right, now this whole story begins by just thinking about 2-to-2 scattering amplitude. So we're going to imagine a 2-to-2 scattering amplitude. Maybe general particles A and B scattering and going to A and B. We think about this scattering as a function of the energies. Lorentz invariant theory, these two Mandelstam invariants, S and T. Okay, and now we want to input what we know just on basic physical grounds about this about the analytic structure of this amplitude. What I'm trying to do here is give you an argument at the level of thinking about the 2-to-2 scattering amplitude for why there's some kind of positivity in the higher dimension operators. The analog of the argument that we did way back here, where we said that there had to be some constraint on the higher dimension operators from this argument of superluminality, the absence of superluminality in the low energy theory. Now, why is this related to anything to do with 2-to-2 scattering? Well, it's for a pretty obvious reason. So if I go back to this picture, remember I said I'm turning on this tiny electric field and I'm looking at the speed of propagation of a photon in this background. Of course, in a field picture, I can think of it exactly the way I told you. Turn on this background and I'm just looking at a propagation, just a 2-point function in this background. But I can also think about this in a particle picture. Lots of very low momentum particles producing this background electric field, and my excitation is just scattering off of it. Okay? And despite the fact that the coupling is very small, the coefficient is small, the energies are small, I'm scattering over and over and over and over again, and that concatenation of all those scatterings is what's building up to give me a time advance or a time delay. Okay, so it's producing this translationally invariant background is allowing me to enhance this very small amplitude by making it happen over and over and over again. I'm enhancing it to get either a time advance or a time delay. So that's why there's clearly a link now between the issue of whether or not there's superluminality in the low energy theory and something to do with the 2-to-2 amplitude. And that something is then reflected in the analytic structure of this amplitude. Okay, so now we know very basic things about this analytic structure. For example, if there's some sort of massive particles in the ultraviolet, then this amplitude should have a branch cut. And the imaginary part of the discontinuity across that branch cut corresponds by the optical theorem to the cross section for producing whatever those states are. The really crucial thing is so therefore we expect that it has branch cuts on the real axis and is otherwise analytic in the complex plane of these variables. The really crucial question is, how do we impose the physics of causality in an understanding of what the amplitude is? And the physical issue is that the amplitude is a process that starts at minus infinity and ends at plus infinity. If someone just hands you the amplitude and doesn't tell you how they got it, what is the fingerprint on the amplitude of the fact that it somehow came from an underlying causal process? And we, as I said before, we still don't precisely know the answer to this question, but there's a limit where we do. And this is a limit where the scattering is very close to being forward. In the limit when the scattering is being very close to forward, you see this 2-to-2 amplitude looks a lot like the propagation of one hard particle in a soft background set up by the other. And so you can relate the question of so this becomes closely related to the question of a 2-point function. And for 2-point functions, we know, again, since time immemorial, what the analytic properties of a 2-point function are supposed to be in order to reflect causality. It turns out that all of this is encoded in a very simple statement that if you hold the t fixed, so holding t fixed, but make f as large as you want, that's going to the forward limit, that in that limit, the amplitude has to be bounded as some power of s. And there are some details depending on whether there is or aren't massless particles like gravity around. But the bottom line is that if you work at a fixed t, but now think in the s plane, that the amplitude should be bounded by s squared, by power smaller than 2. And that then tells us that just by Cauchy's theorem, that I can write a dispersion relation for the amplitude. Remember, t is fixed, so if it's bounded by s to the 2 minus epsilon for some epsilon, I can write it as some constant, something linear in s. And then everything else is just an integral across this branch cut. Okay, so I have a sum of things that look like a pole in the s channel, exchanging some states in the s channel, exchanging some states in the other channel, and the coefficients are just interpreted as a partial wave expansion, as states that have angular momentum s that have spin s. And the characteristic dependence on angle is given by the Lejeune polynomial. And in general D spatial dimensions, these things are called Gegenbauer polynomials. So this term here is just a partial wave expansion. And so this is just a sort of famous dispersion relation for 2-to-2 amplitudes. So again, so the physics that went into this dispersion relation is causality. It's the fact that the amplitude at fixed t is bounded by this power of s, tells us that I can write this dispersion relation. And then, having written the dispersion relation, there are 2 sources of positivity. One is the coefficients here of the partial wave expansion have to be positive. We're interpreting them as the production of some intermediate state. And so these coefficients are the square of something. These coefficients are positive. And the other thing that's positive is the spectrum is positive. The mass squareds here that occur are positive. We're assuming that there's no instability, there's no tachyons. So the claim is that these guys being positive now has some interesting implications in what the expansion of this amplitude is when you're at small s and t. So if you're a low energy effective field theorist, around small s and t, you would do a polynomial expansion of a s and t, and you get some power series in s and t. And the claim is that these 2 positivities, that these probabilities are positive, and that the spectrum is positive, puts many surprising constraints on the structure of that expansion. So indeed, this is the effective field theory expansion. You would take this object and you do this infinite expansion in powers of s and t. I'm going to collect all the coefficients. I can index them by the sort of overall mass scale of the operators, a dq. So it goes like a dq, s to the d minus q, t to the q. So there's a big table of all these coefficients. And the claim is that this infinite table of coefficients are constrained by infinitely many inequalities, linear and nonlinear inequalities.
and they're actually all mixed up in being forced to lie inside a very interesting geometric shape. I won't talk about the systematics of the shape that much, but I'll say something about what the nature of these, at least a simple version of these inequalities are. So one set of inequalities, what we call these sort of Henkel-like inequalities, involve nonlinear relationships between couplings in these rows. Okay, so for instance, these are meant to sharpen the following intuition. Imagine that you have some effective field theory, and you see that there's some dimension 6 operator that's suppressed by the 100 GeV scale. Well, you would expect that the dimension 8 and the dimension 10, the other operators, are not suppressed by 10 to the 50 GeV. Those are all roughly suppressed by the same scale. Okay, so that's one piece of intuition, that there should be some relationship between all the different scales that set the higher dimension operators. Any such relationship must obviously be nonlinear, okay, because we're trying to compare operators of different mass dimension. So that's when I say there are nonlinear constraints. That's what I mean. But there's infinitely many nonlinear constraints that relate operators of different dimension. And then another thing that you might imagine is take a bunch of operators that have the same mass dimension. So that's the things in this red row. And then again, if one of them is one size, the other one shouldn't be a million times bigger or a million times smaller. They should all roughly have the same size. Okay, so those are the two pieces of intuition. But you might think that that intuition is just a reflection of what might naturally happen, and that maybe if you found some system and you fine-tuned and you did this and that you could engineer a factor of 1 million difference between some of these couplings. Okay. Well, that's what we're going to now show is impossible. There are certain things that are just impossible, no matter how you fine-tune, no matter what you do. There are sharp inequalities that force these things to lie inside this geometry. And I should say that over the past year, there have been a number of other groups have been seeing very similar things from complementary points of view. So this is a subject that's been studied in a number of very interesting papers over the past year. All right. The first thing that I want to say just very briefly is that every time you run into a question like this in physics, you see we have a question now where we have some object which is written roughly as a sum over some basis objects with positive coefficients. Every time you run into this kind of situation where you have some object which is written as a sum over some basic ones with positive coefficients, that's telling you that the object that you care about is lying inside a polytope, and that you should think about what that polytope is. Okay, so at the most basic level, imagine that you have a bunch of vertices in some space, and that you want to look at every vector which is a positive weighted combination of those vectors. So here's where the positivity is coming in, that all these weights have got to be positive. Well, that tells you that that all these vectors have to lie inside the convex hull of all these vectors. Let's say instead that you just knew that you had another vector that was a positive combination of vectors without dividing by all the w's. Well, that just tells you it has to lie inside some cone. Okay, so we can either think of it as a polytope, or you can think of it as a cone in one higher dimension. In either way of thinking about things, if you want to check whether some particular, if someone hands you a vector and said, can it be written as a positive combination of these basic rays or these basic vertices? In general, that's not so easy to a check, but the easiest way to check it is if someone gave you the dual description of this cone or this polytope. And the dual description is not as a convex hull of a bunch of vertices, but as a bunch of inequalities that cut it out. So for example, in the case of this two-dimensional polygon, instead of telling you that it's the convex hull of all these vertices, I could tell you that it satisfies the linear inequalities that you're on the right side of this line, that line, that line, that line, that line, and so on. All right, now in general, there's a systematic way of getting the facet structure if you know all the vertices. It's very, it's systematic, but it's laborious. And if you happen to have some classes of polytopes, if you have a class of vertices with the property that you can somehow understand the facet structure analytically a priori,
then something good has happened. And then you can make a lot of progress, because then you can sort of predict ahead of time. You're given the problem in terms of the vertices, but then you can describe it fully in terms of its facets. All right, and I won't go through this in detail, but that's exactly what's going to happen for our problem, where the sort of basic object that shows up and is interpreted in various ways is known as the cyclic polytope, and is an object that's very famous in combinatorics, and which has played an important role in our understanding of the scattering amplitudes in a completely different context in some of the work I was referring to earlier. But the main mathematical point here is that the main surprise is that there's a hidden kind of notion of positivity in these very simple ingredients that went into the dispersion relation. There's a hidden notion of positivity associated with these positive weights over m squared minus s, which is where sort of locality is being represented in this dispersion relation. And there's a hidden positivity associated with the special functions, the Legendre polynomials, and where the positivity of those coefficients has to do with unitary. Okay. So let me just give you some examples of this. The first example I'm going to give is of these infinite set of nonlinear constraints. And to make life especially simple, imagine that I just set t equals 0. And so here is just my very simple model. The amplitude is only a function of s, and it just looks like a sum over m squared of some p of m squared over m squared minus s. That's it. So all I know is I have some function of s that looks like that, but I know that m squared is positive, the m squareds are positive, and the p of m squared is positive. Now I want to know, what does that tell me about the expansion of this as a power series in S? Okay, so if I expand this as a power series in S, well, I have a formula. A0 is given by the sum of p of m squared over m squared. A1 is given by the sum of p of m squared over m squared squared, and so on. All right. So that's the problem. In fact, if I just yeah. So that's a very simple and clean mathematical problem, and it has the following beautiful solution. So we can ask, if you give me this entire list, A0, A1, A2, you give me this vector, how do I know whether this vector can come from a sum that looks like p of m squared over m squared minus s, with p positive and m squared positive? And the answer is the following. This is an if and only if statement. The answer is that you start with this vector A0, A1, A2, and out of it you build the following matrix. It's called the Hankel matrix, whose ij element is little a I plus j. And so it's just the matrix A0, A1, A2, dot, 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 and then you just do A1, A2, A3, A2, A3, A4, and so on. So the claim is that these little a's are consistent if and only if every minor of this matrix is positive. Okay. And in fact, if you those are the infinite set of constraints that I was alluding to earlier. If you happen to know more, if someone tells you what the gap is to the lightest state, then you can say even more constraints. I don't have time to explain this in detail, but just to give you an idea. The simplest versions of this are very easy to see by hand. If I, for example, the most simple thing of all is that just all these a's are positive. Well, that's obvious. If I take any a, A0, as you just said, is sum of p of m squared over m squared. All of them are just manifestly positive, and so that is the positivity of the coefficient to the f to the 4 term that I was mentioning very early on is just the most trivial example of this constraint. But there is an infinite series of nonlinear constraints that generalize beyond it. The first nonlinear case is something like A2, A0 minus A1 squared is positive, and that is a sort of trivial consequence of the Cauchy-Schwarz inequality. You can really think of this as just a giant generalization of Cauchy-Schwarz, but sort of very nicely given as the minors of this Hankel matrix being positive. All right, that's the first kind of constraint. There's a second constraint. There's a second positivity. So if we go back to this expression for the dispersion relation, now we want to see how it depends on t. So I have to do an expansion of these Legendre polynomials, or these Gegenbauer polynomials. And so that's going to pull down, no need to look at this in any detail, but this is going to pull down derivatives
of this Gegenbauer polynomial. Okay, so now my coefficients, and now the coefficients of the couplings that all have the same units lie in the convex hull of vectors that are given for a given spin by derivatives of the Gegenbauer polynomials, all evaluated at cos theta equals 1. All right, so again, this is a convex hull problem, but with infinitely many vertices, because for every spin in this partial wave expansion, I have a given vector. So in principle, this sounds like a very hard problem. How do I figure out whether or not a given vector is in the convex hull of an infinite number of vectors? But of course, in physics and math, we never get random crap. And the reason we can do this is that this again is an example of a cyclic polytope. So this is in a sense the sort of nicest possible vectors they can be. We know everything about their facet structure ahead of time. And in fact, this is a general statement, not just true for Legendre Gegenbauer polynomials. It's equivalent, not exactly the same, but equivalent to a result that was first proven in the mid-1960s. That's actually true for any orthogonal polynomial with respect to a positive matrix. Right, and there's even more hidden positivity that further constrains the story. So this is essentially the physics of now of unitarity that tells you that all these coefficients have to lie inside this particular polytope. On top of that, we can sometimes have constraints from crossing symmetry. If we have identical particles, then we know that we should be able to expand the same amplitude either in the S channel or in the T channel. And so in the language of these coefficients, there has to be a symmetry that exchanges S and T. So that tells me that all of these coefficients of S to the P, T to the Q have to be symmetric under exchanging S and T. So that means that they have to lie on a plane. They have to lie in a plane in this space. We already know they have to lie inside this interesting polytopal shape cut out by all these inequalities, but on top of that, they have to lie in a plane that puts a further bigger constraint on them. So schematically in a picture like this. So the first thing that we learn is that they live in this sort of unitarity polytope, but they also have to be crossing symmetric, and so they end up lying in this plane. All right, and we can take all those things together and make sort of detailed predictions about what 2-to-2 scattering amplitudes can look like in the real world. And it's either statements that would be true of sort of quantum gravity in the real world. Again, these are tiny higher dimension operators. Nobody cares about them experimentally. No one's going to measure them anytime soon. But there are things that we can predict ahead of time. And there are nice, small, bounded regions. Okay, so I don't have time to explain to you exactly what I've drawn here, but we're looking at the coefficients of various higher dimension operators involving photon and graviton scattering, and taking ratios of them, and ratios of them are forced to lie in these very specific regions, okay? Very specific analytically determined regions. Okay, so that's an example and as I said, that this is the two-dimensional example, but there are 3, 4, again, there are infinitely many constraints on these higher dimension operators. Okay, so a couple of comments. One of them is that just to relate this to the discussion of superluminality that I mentioned at the beginning. So I told you that we can think of the propagation of the particle in a background as many soft collisions with the background, and so that's what relates the physics of the 2-to-2 amplitude that we just talked about to the superluminality discussion. Well, it turns out I won't go through this in detail, that you can talk about a more general blob instead of talking about this perfectly translationally invariant blob. You can really talk about any old blob with some characteristic size r, and if you ask that propagating through this blob only gives you a time advance, gives you a time delay and not a time advance, then you learn not only that the coefficient of the 2-to-2 amplitude at 0 should have some sign, but you learn something about this whole derivative. So the more general statement is that this amplitude divided by s, negative a of s over s, should be monotonic. This, in fact, follows from the dispersive representation. Okay, so this shows even more precisely that the existence of the dispersion relation that's only inputting the statement about the asymptotic behavior of the amplitude at large s, which is supposed to abstractly tell you about causality, is indeed exactly matching what you want for the absence of superluminality as seen in the deep infrared, not just in translationally invariant backgrounds, but a little bit more generally. And the second comment is that these are, as I said, there's a huge number of constraints. There are these sort of finite regions that all these higher dimension operators can live in. But when you actually look at where real theories land in these spaces, you find that they're occupying even tinier regions than are allowed by the constraints that we're talking about so far. And the reason is that there's a big missing ingredient in all this in all the discussion we've had so far, which that we have input the physics of causality by looking at by writing dispersion relations at fixed t. We've input the physics of causality, but we have not yet input the sort of crucial constraint that the amplitude is well behaved at high energies. Like, in other words, high energy fixed angle scattering doesn't violate unitarity. And that's related to the fact that that we expect that when we do these partial wave expansions, that the coefficients of higher and higher spin in the partial wave expansion should be physically suppressed. But that information is nowhere in any of the analyses that we're talking about so far, and it's a conceptual obstruction to figure out how we can input into this discussion more information about UV completion. But just so you have an idea, here's an example of the kind of what the region looks like on general grounds. This is some specific example involving graviton scattering. Again, I won't explain it in detail, but this is what it can sort of look like in general. Some region like this, and then you take, gravity scattering amplitudes in healthy theories that we know in string theory, many different kinds of string theory, and they're all piled up down here. They're not remotely exploring all the space available to them. They're all piled up down here, and the reason is that that somehow that most of the space is being dominated by would-be theories that would have large partial wave coefficients for large spin. And somehow they don't seem to be consistent. We don't seem to ever see them in concrete physical systems. So this is something to be understood more. Okay. So Jubin, I think we are now at the 90-minute mark.
Yes.
Shall we clap now?
Yes, I can clap first. But it really it's up to you. Say whether you want to convey some ideas to maybe quantum matter audience, and the video is recorded, so it's up to you.
All right. I think I probably have around 15 minutes for the second part, but it's a really simple, but I think a very striking thing, and it's another aspect of the sort of the IR UV connection involving gravity, which I thought it's a physical thing, and yeah. I'd be happy to talk about it if people are interested in hearing about it.
Yeah, so just up to you. Certainly you can.
Okay.
People will stay if you want.
All right.
It's up to your time. Thanks.
All right. Very good. All right. So I'm going to keep going. All right. Okay. So so now the topic is what I've written is strings and the IR challenge of UV completion. And here I want to begin with a simple question, which is that why is it that gravity, which is the most, this is a question that you might have had in high school. Certainly I had in high school. Why is gravity, which is the most obvious force of daily macroscopic life, why is it the one that's hardest to UV complete? Okay, in high school I didn't know what UV complete meant, but I basically knew what it meant. I basically had this question in high school. So why is it that this most obvious force of daily macroscopic life is the one that's hardest to UV complete, while we've had these much more fancy interactions like the weak interactions, subnuclear scales, operating on subnuclear scales, they were discovered roughly in the beginning of the 20th century, and they're UV completed 2/3 of the way through the 20th century. So they're discovered in UV completed in 70 years, but gravity, which we've known about forever, we still don't know how to, we still are struggling to think about how to UV complete. And there is a great answer to this question, and it's another aspect of this UVIR connection, right? So in order to explain why, let me contrast the situation with other theories that we know how to
UV complete. So imagine that we have pion scattering, okay? So, or Goldstone scattering in general. Here, the low energy amplitude, there's a dimensionful coupling constant, and the low energy amplitude grows like the square of the energy. Okay, so the 2-to-2 amplitude grows like the square of the energy. And so, okay, that's a classic problem. The amplitude is growing with energy, and so you need to stop that from happening. Okay, but now instead of writing down a Lagrangian and thinking about spontaneous symmetry breaking and Higgses and this and that, I can just play and say, okay, I'm just going to fix the amplitude somehow. I'm going to just write down a different function that is small when I go to infinity, and that's it. Okay, so let me try to do it. Let me just try to change the amplitude. So I'm going to do it like this. Where I had s, I'll multiply by s over 1 minus s over m squared, and then for t, t over 1 minus t over m squared. All right, great. Now clearly, as I go to large s and t, so long as this capital M is smaller than f, this amplitude is a small number, and so I've solved the problem. However, now I have to check something, because by putting this guy down there, I have now introduced a pole. I've introduced a pole at s equals m squared, and so now I have to do a check. I have to check that the residue on this pole is appropriately positive. That I can interpret the residue on this pole as the probability for producing the intermediate particle as a resonance. This is exactly the same positivity criteria that we're talking about in our dispersive analysis a moment ago. Okay. Now in this case, it is. That's because of this thing, so this overall minus sign out in front, the residue on the pole when s equals m squared is a positive number. And so this is compatible with unitarity, and then there's nothing obviously wrong with this amplitude. This is in fact precisely the UV completion of this amplitude that you'd get if you got this nonlinear sigma model from a linear sigma model, and capital M would be the mass of the Higgs. Except I don't have to do any of those things and talk about Goldstone's theorem and the Higgs and Max and half potential and all that stuff. Just by playing, I just write down the right answer. So this is a trivial tree level UV completion. Okay. All right, now let's try something else. And in fact, the issue doesn't especially have anything to do, the issue I'm about to tell you is not unique to gravity. I'll begin actually with a slightly simpler example where we imagine we're just talking about a simple scalar theory, but with a cubic interaction, phi-cubed interaction. Now, once again, the 2-to-2 amplitude starts off as g squared 1 over s plus 1 over t plus 1 over u. Okay, now here, in this example, it does not appear that you need to UV complete it because the amplitudes are dying with energy. But in sufficiently high dimensions, this dying with energy is still not fast enough. So for example, in 7 dimensions and above, this would still need to be UV completed. So I'm just doing this in order to avoid, for the moment, any even tiny complication involving graviton polarizations and so on. Everything I'm talking about is equally true for Yang-Mills and gravity. So let's say that your mission was to just build some amplitude, play the same kind of game, build some amplitude, which just dies even faster than 1 over s, than 1 over energy squared as you go to high energies. Okay, so why don't we try the same game? I will just put in 1 over s, and then down here I'll put the same 1 minus s over m squared, do the same for t, do the same for u. And now you immediately run into an unpleasant surprise that this is definitely violates unitarity. Why does it violate unitarity? Because now you see the residue on the pole at s equals m squared now has a negative sign. Now, why didn't we have this problem before? We didn't have this problem before because there was an overall minus sign in front of the whole amplitude. In fact, if I didn't know the sign in front of the whole amplitude and I played this game, I would discover, oh, I can only get this putative UV completion to work if the sign was negative. That's one of the ways to discover this sign. And that's in fact exactly what we were just talking about in the previous part of the talk. Okay. But what is the difference here? The difference is that here and now the sign, in other words, here we didn't know ahead of time what to expect for the sign of the amplitude. It's some contact interaction. We don't know ahead of time what to expect for the sign of the amplitude, but it's not true here. Here we know what the sign of the amplitude is at very low energies, precisely because it's coming from the exchange of massless particles. Okay, so in other words, the fact that we have massless residues corresponding to massless particle exchange forces
that any UV improvement of this amplitude with simple polynomial factors downstairs is forced to have some residues with the wrong sign. In fact, it's a trivial corollary of just Cauchy's theorem. We are trying to get something which dies even faster than 1 over s. Anything we do, any rational function of s that we put any polynomials upstairs and downstairs, if it's going to die faster than 1 over s at infinity, that means that the sum of all the residues is got to be 0. And since we know that the residue at s equals 0 is positive, since it's associated with massless particle exchange, that tells you that some of the massive residues must be negative, right? So that's really interesting, that we can't just sort of trivially UV complete, UV improve this theory in the same way that we could UV improve that one. And why? It's precisely because this second theory already has massless exchanges for the 2-to-2 amplitude. In other words, it's precisely because the leading interaction for 2-to-2 scattering involves a long-range force. Because it involves a long-range force, it already has some positive signs associated with it that force a trivial UV completion like this to violate unitarity. Whereas the previous example, we didn't know anything a priori about the sign of this sort of contact interaction, and all we learned from this argument is what that sign has to be. So the very fact that there is a long-range force is what makes it, the long-range interaction is what makes it impossible to sort of trivially UV complete these theories in this way. So if I say it again, it's theories that have a fundamental 3-particle scattering, a fundamental 3-particle amplitude, then have the property that the 4-particle amplitude have infrared poles, and that makes it impossible to find this kind of simple tree-level UV completion with, like the sort of Higgs example, with a finite number of particles and poles. And in fact, it's simple to prove that you have to have an infinite tower of masses and an infinite tower of spins. Not only do you need infinitely many masses, you also have to have spins that are that go off to infinity. So I haven't said anything about strings yet, but this is already something qualitatively stringy that we have learned just from these very simple considerations. The only assumption that's going in here is that the kind of UV completion I have is looks like it has a weak coupling, so it begins with an amplitude that only has poles rather than something sort of more complicated that would have branch cuts and so on already. But if we have something that only has poles, and again, at least in the standard model, this is what we see. That's the story of the Higgs, is exactly a kind of trivial UV completion of this sort. String theory is an example of a UV completion of this sort. And we're saying that if we're talking about any theory that has long-range interactions, then it's impossible to sort of complete it in this way. And any completion has to involve an infinite tower of masses and spins. So that's the answer to the high school question, why it's hard. So it's something about the IR properties of the theory, thanks to the constraints from causality and unitarity, that tell you that the UV has got to be much richer than you would have naively thought. And in fact, you can proceed in this way to discover just if you follow this philosophy and just play, you just to make guesses for amplitudes, you now know that you have to have an infinite tower of particles. Essentially, the first guess that you'd make for an amplitude involving gravity would give you the string amplitude. Okay, so you can really bottom up, trip over discovering the string amplitudes in this way. So, so here I just need to tell you something. If you haven't seen this before, this might look this might not be familiar. But this is what the 2-to-2 gravity amplitude looks like in just ordinary gravity. Okay, never mind what these symbols are. This is written in 4 dimensions, and these symbols are roughly the square roots of the momenta of the particle. So they're called spinor helicity variables, and they let you keep track of the polarizations of the gravitons in a simple way. So here we're talking about the scattering of this particular polarization state for gravitons. But the crucial thing I want you to notice about this 2-to-2 amplitude is that it does not look like the sum of something in the ST and the U channels. It's the product of something in the ST and the U channels. And the fact that the 2-to-2 amplitude is not naturally the sum over 3 channels, but the 3 channels come together, again, this is even in ordinary gravity, this reflects the fact that when you attempt to describe gravity using a Lagrangian, you need gauge redundancy and so on. Okay, that every Feynman diagram by itself is not gauge invariant, only the sum of all of them is gauge invariant. And here we see the most invariant content of that fact is that the actual amplitude does not split into a sum over the channels, but sees all of them in a big product. All right, well, let's say that you begin with this, and now you want to play the game that we talked about before, that I want to now complete it. So I'm going to take this thing before, and now I'm just going to multiply it by some gigantic object. Since it's symmetric in ST and U, I'll just write down all the poles downstairs, some pole in S and T and U. And clearly there's got to be some numerator here as well. Why does there have to be a numerator? Because if there wasn't, if I sit on a pole in S, then the residue of that pole will not be a polynomial in T. And T is basically cosine theta, is related to cosine theta. So we want it to be a polynomial in cosine theta because the order of that polynomial will be the maximum spin of the particles that we're seeing. If it's not a polynomial, that means that on any one of these resonances, we already have an infinite number of particles, and we definitely don't want to have that. So that's a big constraint, is that on a pole in S, the result has got to be just a polynomial in T, or in cosine theta. So that tells you that this numerator should have a lot of zeros in order to kill these bad polynomials down there. And it's really this three-line argument that I won't go through now, but you can look at the slides later and just do yourself, is that there's an essentially certainly by far the simplest solution for the choice of the roots of this polynomial in S, T, and U upstairs. If you just demand that those roots are only there in order to kill these bad poles and avoid this the difficulty that I mentioned, you arrive at this expression. And that's the famous Virasoro-Shapiro amplitude. That's the amplitude in type 2 string theory for gravity, for graviton scattering. Okay, so I'm not saying this is not a derivation, because no one says that we have to have the simplest possible numerator and it should do all these things. But I'm just trying to show that this is a way that you could sort of trip across the stringy amplitude from this very simple point of view. Now, in fact, what's really miraculous about the string amplitude, really miraculous about the string amplitude is the following. So if I go back to this expression, you might even ask, maybe could it be that this is the unique possible, this is the unique formula that has the property that it does everything that you want at fixed values of t. It satisfies this causality constraint that it's bounded by S squared, and that on all the poles it has an expansion in terms of Legendre polynomials with positive coefficients. It turns out that the constraint that it satisfies, the causality constraints and so on, those are really easy. The real miracle is that this object satisfies the positivity condition. And in fact, if you sit on a pole, these gamma functions have poles, and those poles correspond to the massive string state. So if you sit on the nth pole, and you look at what the residue of the amplitude is as a function of the scattering angle, the function of cosine theta, you get this very simple polynomial in cosine theta. Okay, it's basically a polynomial that has evenly spaced roots between -1 and 1 in steps of steps of 2 over n. Okay, so just this polynomial with evenly spaced roots. Now, and in order for this to be physical, in order to be unitary, you have to be able to expand this polynomial as a sum over Legendre polynomials with positive coefficients. And this is absolutely not obvious. So this is a totally miraculous fact. In fact, already at the third level here at n equals 3, this is the polynomial you get, cos theta minus a third times cos theta plus a third, which is cos squared theta minus 1/9. You might remember that the Legendre polynomial in 3 dimensions looks like cos squared theta minus 1/3. In d spatial dimensions, for spin 2, in d spatial dimensions, it looks like cos squared theta minus 1 over d. And therefore, this guy here, cos squared theta minus 1/9, looks like it has a spin 2 part, which is cos squared theta minus 1 over d. But then to get the rest, it's got to be plus 1 over d minus 1 over 9. This looks like it's spin 0. It's just a constant. but you'll notice that this would be negative if little d, which is the number of spatial dimensions, was bigger than 9. And therefore, we discover that we have to have less than or equal to 9 spatial dimensions. That's a discovery that string theory only makes sense in 10 dimensions. And it's sitting there in this positivity check on this amplitude. And in fact, so that already tells you something amazing, that this expression only makes sense in less than or equal to 10 space-time dimensions. But beyond that, the fact that this polynomial is a positive expansion for all higher n is just an amazingly it's a statement you can tell a high school student, but it's an amazingly non-trivial statement mathematically that still does not have a direct proof. There are, of course, indirect proofs of this fact from the consistency of string theory and the so-called no-ghost theorem, but it's an extremely simple fact that deserves probably an extremely simple proof. And actually, some of our wonderful postdocs at the Institute have actually found a proof that works up to 6 spatial dimensions, but still there's something, 6 space-time dimensions, but still some new ideas seem to be needed to go all the way up to 10 space-time dimensions, where we actually know that it's true. Okay, so the reason I'm telling you all of this is first, there's just this qualitative fact, again, another aspect of this sort of UV IR connection, that for why it's difficult to UV complete gravity and Yang-Mills theory and even phi cube theory in high enough dimensions, that anything with a long range force has to have a very fancy UV completion relative to kind of simple things that don't. And B, that finding that the real miracle of this consistency involves, again, some deep sort of positivity whose origin I think we need to understand in as many sort of new ways as we possibly can, because these are really miraculous statements, and when we have simple miraculous statements in physics, we should really try to understand them in as many ways as we can. I should say though that for this kind of question of whether this amplitude could actually be unique, already a number of years ago we discovered some funny deformations of these amplitudes. I've given you an example here. That if you add to this amplitude some epsilon times what looks like a little modification of it, then if this epsilon is not too big, and it definitely starts to look like these gammas, it's not far from the original structure. You like lots of things you can do in this neighborhood just immediately screw up this positivity check. But we did find some funny deformations of these amplitudes, where if you're the only thing that you're checking is the consistency of the massless 2-to-2 amplitudes, there are things which are consistent and deform away from the stringy result. So this suggests that if we want to sort of pursue this program, we have to also think about the consistency of massive scattering as well, not just the massless consistency, but the consistency of the new massive states that are introduced in this UV completion. That's not too surprising. That's exactly what happened in the story of the weak interactions, for example, where we began with the Fermi interaction, which was UV completed into having a W, massive W particle, but then you have to think about the scattering of the massive W particles, and you discover that the longitudinal components of a massive W's give you growing scattering amplitudes, which in turn have to be UV completed by adding the Higgs, and only after you've done all of that are you done. So it's likely that that one would have to ask this kind of question here as well. So I think this is a very interesting direction to try and pursue. And again, in all the stories that I've been telling you, there's a sort of fascinating interplay between basic assumptions about what the physics looks like in the deep ultraviolet, associated with the polynomial boundedness for the amplitudes and simple analytic properties, and surprising constraints that we can extract from that for low energy processes on the one hand, and on the other hand, the very existence of the infrared poles force any putative UV completion to already at first blush be in the kind of world of infinite masses and infinite towers of particles with infinitely high spins. and sort of heading in the direction of something that is stringy. Okay, so so maybe with that I will end and see if there are any questions.
Okay. Yeah, thanks very much, Nima, for the nice lecture and seminar. Any question from the audience, please? Yes, Sunset, please go ahead.
Hi, thank you for the interesting talk. So if you drop Lorentz invariance but keep only the causality and unitarity, can you derive such bounds?
It's a very good question. So I think the real question is, and that's actually, yeah, that's the discussion that I wanted to have is what if anything are the avatar of these kind of statements that we could have in non-Lorentz invariant systems. I think the main issue is what the analog, I mean, the main technical issue is there some sort of known analog for the for some asymptotic boundedness of 2-to-2 scattering? If there is, then you could get started. In other words, if you could get started with a dispersive representation, then it's very likely that you could say something. But here it's really on the other hand, in all the examples I know, it's not approximate causality. It's sort of rigorous causality, which tells you that you have analytic behavior in the complex plane. So it's if you have a 2-point function which is sort of rigorously 0 for t less than 0 and turns on for t bigger than 0, then you know that it's that the Fourier transform is analytic in the upper half plane. Of course, we expect causality in general. That's but if we now want to port that to a statement about amplitudes, what's giving us these sort of sharp, powerful things here is the analog of that is that precise 0 outside the light cone. So you want to say that you have some exact 0 outside the light cone, and that exact 0 is turning into some statement about the analytic structure of amplitudes. Yeah, so I think if there's some useful analog of that in non-relativistic systems, I don't know what they are. I'm sure there are people who've written papers on it. I don't myself know what they are, but that's that would be the place to begin.
Mm-hmm. Thank you.
But you see, it doesn't. I mean, the reason I'm a little skeptical is it doesn't have this sort of. I mean, if we forget all the technical reasons for this, the physical reason this happened is again, why is it that we normally? I'm just going back to what I said at the very start. Normally, you think, well, in order to learn something about a higher dimension operator, you've got to do a super precise, difficult, accurate measurement, right? Or you have to find a situation where it violates some property of the low energy theory. So, in particle physics, we look for higher dimension operators suppressed by the gut scale that might give us proton decay. Even though it's tiny, it's the leading thing that would give you proton decay. Well, the analog here is that there is something in the low energy theory which we know exactly, which is that the things propagate exactly on the light cone. And because of that super sharp statement, then we're sensitive to like tiny corrections. And so that's why we can say anything. I think the moment that there is some sort of fuzziness in that notion of what signal propagation is, it sounds hard to learn something, at least at something comparably powerful.
Mm-hmm.
There's also a question from JC Strickland. JC, please go ahead.
Yes, hi. Thank you for that really interesting talk. Could you go back to the slide where you were showing the polyhedron with the cross section?
Sure. This one?
Yeah, that's the one.
Yeah.
So basically, all of these inequalities and constraints that you're talking about are reducing the number of degrees of freedom of an infinite set of coefficients, right? Do you have reason to believe that there's actually really only a finite number of degrees of freedom in them, or do you think that it's still infinite?
No, I think it is still. I mean, I think we know it's still infinite in the sense that we know that these are just constraints that are. These are such broad constraints that they are coming. That you know any consistent underlying Lagrangian theory will satisfy them. Okay. So in that sense, we already know there's an infinite number of knobs I can turn. So there isn't some sort of finite dimension. There isn't some finite set of solutions to literally the problem that we're asking here. What's surprising is that despite the fact that there's a sort of continuous infinity of possibilities, when you look at them in this space, in the space of the ratio of these couplings and so on, they populate these tiny regions. That's the surprise. And you know, if you didn't think about these things, you just think, yeah, okay, there's these infinite many couplings. You can plot them. They can be anything you want. If you fine tune hard enough, you can make one of them 3,000 times bigger than the other, and so on and so forth. But no, they have to live in these little tiny little regions. You know, if you and on top of that, even the constraints that we're talking about, which are already, as I said, they're already pretty constraining. If you look at real physical theories, they're even more constrained than that, and we don't understand that yet. Okay, so that's the example I was showing you here, that this is an example of what the sort of whole region might look like. It's definitely not the whole white region. It's definitely not even, you know, the blue region is sort of what's allowed by what we now can sort of prove rigorously. But real theories are piling up. They're not on top of each other, of course, you can tell them apart, but they're piling up in tiny corners here. So there's clearly still more that we don't understand. And again, just to push the point, let's say some experiment, I mean, this is not going to happen in my lifetime, but let's say some experimentalists actually found some of these higher dimensional operators and they found you're in here somewhere. Okay, then nothing about like physics as we know it, you know, no experiment is going to go wrong right away. Everything is like Lorentzian variant, higher dimension operators, everything looks normal, but you would instantaneously know that there's something about our basic assumptions. I mean, something about the like basic structure that I was telling you about in the first part of the talk is just wrong, right? That we cannot possibly get that from I mean, if you got something out here in the white, then we would know it's just wrong. So it's possible for measurements of higher dimension operators, which are indeed probes of high energy physics, they can, not everything that you measure is compatible with something that's okay with these ideas of Lorentzian variant causality and unitarity. Did that answer your question?
It didn't really give me clarity on whether or not, I mean, so surely there are like many, or there's an infinity of different possible solutions, but whether or not like the degrees of freedom within those, like your polyhedron is being brought to a lower.
That is also infinite, because we really have it. I mean, it's really that, and what I'm drawing is, I mean, all of these things are cross sections of some infinite dimensional object, of course, because I have infinitely many coefficients. So I have infinitely many coefficients. The object is definitely infinite. Now, but having said that, there are interesting cases where, despite the fact that the object is formally infinite, you might discover that if you plot a whole bunch of the coefficients, they actually lie on a much lower dimensional locus. Okay, and that can be a signal that the UV completion is especially simple. I don't have time to explain it, but you know, in some situations, you might find that some of these coefficients lie on the low dimensional loci in the high dimensional space, and the dimensionality of the locus is a reflection of how many particles you're integrating out in the ultraviolet, for example. Okay, so if you have an especially simple situation, the simplicity might show up in the fact that there's a surprising, there is some surprise that they're not filling out the entire space available to them. So there's a lot more structure in there, but no, but on general grounds, they are infinite. Everything is infinite, and you can, in principle, the sort of the continuous diodes that we can tune that definitely produce consistent that fill out this space definitely allow all the dimensionalities to be probed.
Thank you.
Wait, oh, Junwei Chen has a question, please. Go ahead.
Yeah, do your conclusions depend on the theory is perturbative?
Which conclusions are you?
Well, I am asking a general question because it seems you talk about tree-level diagrams.
Right.
But if the theory is non-perturbative, then whether anything will be, any conclusion will be modified.
I'll just say a couple of things about this. When you talk about first, we're always imagining a situation. You see, whenever you talk about a scattering process, period, there is something that's weakly coupled there, because after all, if there's nothing weakly coupled, the particles don't escape to infinity. Okay, so the very notion of a scattering process has some notion of a weak coupling built into it. In the real world, we can talk about scattering photons, gravitons. These are all particles that are super weakly interacting at long distances. And if they didn't, if instead you had some sort of conformal field theory, some strongly coupled conformal field theory, then there is no S matrix officially in a strongly coupled conformal theory, precisely because as the particles are going out to infinity, they keep radiating and radiating and radiating, and so there's no well-defined amplitude. So built in, so just ab initio, built into the whole question, I was assuming that. You could, on top of that, in the first part of what I was talking about with all these higher dimension operators, you could ask about whether I'm assuming something about weak coupling or strong coupling in the high energy theory, in the full theory, and there is a kind of there is a mild assumption that there is some kind of weak coupling, not like, for example, if we're talking about graviton scattering amplitudes, then I want to talk about the higher dimension operators involving gravitons. The very notion of a higher dimension operator coming from integrating out massive modes assumes a degree of weak coupling, because if you don't, then you can't say, oh, I have some R to the fourth term, for example, because the R to the fourth term is actually generated by logarithmic running of massless graviton loops in the low energy theory by itself. That higher dimension operator is actually running in the low energy theory. And so if there's no weak coupling at all, then there's no way of separating what part is coming from the high energy states and what part is coming from the massless running in the low energy theory. So you need some kind of a weak coupling of the stuff that you're scattering to whatever's going on in the UV completion, even for the notion of a higher dimension operator to sort of be well defined. Of course, the stuff itself could be arbitrarily strongly coupled with itself. You know, so we could have sort of gravity coupled to some massive sector of some crazily strongly coupled stuff to itself, but the coupling to gravity should have some should have a weak coupling associated.
Thank you.
Thanks for the nice question. Any other comments? Questions? Sunset has another one.
Yeah, I have another question.
Yeah,
so
please.
related to the previous one. So if one includes a massive but extended object, how would that change your conclusion?
Doesn't at all. In fact, it applies to string theory. All these constraints apply in string theory. Sorry, I'm not sure. You mean if we add those things as kind of massive states?
Yes.
Or yeah, no, then we're nowhere assuming anything about whether it's point particles, nothing. In fact, as I said, that some of the most interesting examples of things that satisfy these constraints come from, you know, perturbative string amplitudes. In fact, that's how string theory was discovered, was exactly in the context of this S matrix program, right? So these were exactly the kind of questions they were asking when they ran into string theory. So they, when you have field theoretic UV completions, interestingly, they tend to like not explore the kind of full space of what could be consistent in the UV. So all we know, for example, from causality is that there has to be this regime when T is fixed and S is large, where the amplitude is bounded by S squared. That's it. We don't have to have the amplitude is bounded by polynomial everywhere, nothing. The only thing we know is that at fixed T, large S, the amplitude should be bounded by S squared. Field theory is way generous about this. It says that's bounded by polynomially everywhere. Everything dies as a polynomial. Polynomials everywhere. It's not needed. And string theory is more economical. String theory is exactly polynomially bounded where it needs to be, and elsewhere it's either exponentially dying or exponentially growing, depending on where you are in the kinematic space. So, nowhere in we're not making any assumptions about the ultraviolet in any of these arguments. And in fact, again, this is one of the I'm just repeating myself over and over again, but this is one of the fun aspects, one of the sort of deep aspects of this UV-IR connection is that is you can see many, if not, you can't see all of these constraints so far, but we can certainly see some of the most basic ones by these purely infrared arguments. It says nothing about these UV states and boundedness and blah, 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 dispersion relations, just a super simple thing. I have a low energy theory. I turn on this minuscule electric field, and the fact that I shouldn't be able to go faster than the speed of light tells me something. And so that shows that whatever's going on has very little to do with any detailed knowledge of what's going on in the UV.
Suppose I tune the mass of those extended object like string all the way to tensionless limit.
Oh, then things are different, of course. Then the whole thing is different. Yeah. So we're certainly assuming that we have a finite number of states that we're scattering. In my physical argument, in my simple physical argument, of course, if you tune them down to arbitrarily light, then I can't turn on even an arbitrarily tiny electric field without making them. And then so I don't know that I have that background. So already in that simple physical example, obviously, I'm assuming some kind of gap to where the other guys are in order to be able to run this argument.
So as far as gap is non-zero, that's fine. Is that what you need?
Yeah. Yes.
Mm-hmm.
And I mean, a little bit more precisely, we're talking about scattering massless particles. So really, sort of physically, it's a gap to the stuff that's there in the UV completion. But the particles themselves are massless. Okay, so that there is no gap. But the sort of gap to where the new states in the UV, we need some gap to where the new states in the UV completion come in.
But no matter how many gapped states there are, that doesn't.
That's right, exactly. It makes no difference. Yeah. And that showed up also technically. I mean, I skipped these important technical discussions, but when I wrote that dispersion relation, I just assumed that I just asserted the picture looks like this is a branch cut that starts at some large mass. Well, that's not true because there's massless particles. Of course, there's a branch cut that comes all the way down to the origin. But again, if there's a gap to the massive states and there's any weak coupling involved to the massive states, the massive states could be extremely strongly coupled amongst themselves, but they need to have a weak coupling to the state that we're scattering. Then the extra contribution from the sort of branch cut at low energies is irrelevant compared to the leading one that I'm keeping in that picture. But anyway, this is really all the physics of in the picture of turning on a tiny electric field. I have to have the stuff, my photon is free. My photon is free at long distances, and there is some energy I get to go up. There's some energy I can go up to where it's approximately free, and then something interesting happens to it. And if there's any such gap, then I will turn on my electric field with an arbitrarily tiny amplitude compared to what would excite this stuff, and I can run the superluminality argument and learn what I learned. And all the stuff with the dispersion relation, I should say that it is one of the interesting things in this business is that to begin with some of the simplest things, you see a statement that you can kind of learn from these simple infrared arguments involving causality and so on. And then there are these things you learn from dispersion relations. And at the moment, they're not symmetrical at all. At the moment, we seem to learn vastly more from the dispersion relations than we can explain from sort of infrared causality arguments. So there seems to be some asymmetry. I started off with this very simple picture about the light cone and so on, and then I switched to this dispersive argument. And I justified it by saying, well, it's the same thing, right? We're learning about the 2-to-2 scattering in both cases, but somehow from the dispersive point of view, we get these infinitely many coefficients, all these, fancy bounds and all this interesting geometry. And at the moment, I don't know how to understand if it's even possible to understand those things from some kind of long distance perspective. But perhaps there's more interesting kind of backgrounds that we can generate that can be sensitive to these via time delays to these more and more interesting, that can be sensitive to these more complicated constraints. I can't imagine what they are right now, but that's a kind of a mismatch in this subject. It would be very nice if those two things actually matched up more precisely.
Okay. Yeah, I think it's pretty much take a lot of time from Nima already. I think he has a very busy schedule, so we should just thank Professor Nima Arkani-Hamed for taking giving this nice seminar, and we are happy to have him today. Thank you very much.
Thanks a lot, Zubin. Thanks a lot, guys.
Thank you, Nima. It's a pleasure. Thank you very much.
Thanks.
Bye-bye.
Thanks a lot.
Thank you.